Okay, so this is the next one, 59. Here we are given an integral domain R in which these two equations are true. That is, if we add 20 copies of the unity 1, then we get 0, and also at the same time if we add 12 copies of the unity 1, then also we get 0. And we have to find the characteristic of R. Okay, so let's see the solution. Keep in mind R is an integral domain. So we already know from a result in the text that its characteristic is either going to be 0 or a prime number. In this case it won't be 0 because we already have this fact. That is, the additive order of 1 is finite in the ring. And we have to find the additive order. And from another result we also know that in a ring in which there is a unity, its additive order is in fact the characteristic of the ring. So let's see what we can do with these two equations. Since (20.1) is 0 and 12.1 is also 0, we have this. (2.12.1) minus 20.1. It will also be 0 because it's just 2.0 minus 0. Or if you manipulate this using the laws of exponent in the additive group of the ring, then you get 24 minus 20, which is 4. And I hope you understand how exactly we are getting this from this. That's because if you do not use this notation and you use the usual multiplicative notation in a group, that is, if you are treating the unity 1 as an element in this group, an element in this additive group, and you use the multiplicative notation from group theory to write this equation, then the same equation will look like this. Okay, and then you use the two laws of exponents and you can write this. So that's why I say that we are using the laws of exponent. And in the multiplicative notation, in place of the identity element 0, you can just simply write the E. E of course is 0 in this group, but that is E. So this becomes equal to E then, and which just simply means that the fourth power of 1 is equal to the identity. This same equation, when you write in our notation, it looks like this, and which all of these things just simply mean, both this as well as this, they mean that 1 plus 1 plus 1 plus 1 is equal to 0. Okay, that's what it means. In fact, that's why the author has reminded us of the meaning of n dot 1. Now, from this thing, what we see is that the additive order of 1 in this group has to divide the exponent. This is one of the properties that we already know from group theory. So we can write that. Hence, the additive order of 1 divides 4. And we also know from a result in ring theory that we already have seen in the text that this additive order is in fact going to be the characteristic of the ring. And because the ring is an integral domain, this characteristic is either 0 or a prime number. It cannot be 0, that we can see now. So it has to be a prime number. Since this additive order is the characteristic of R, and R is an integral domain this order must be prime. It is either 0 or prime, but 0, of course, it's not 0, so it has to be a prime. And there is only one prime that divides 4, and that is 2. Hence, the additive order of 1 will be 2, and hence the characteristic of R is also 2. We can just directly write, hence R has characteristic 2. So that's how we have found the characteristic of R. Let's now see the next one. The next one is this. In a commutative ring of characteristic 2, prove that the idempotents form a subring. In a commutative ring of characteristic 2, prove that the idempotents form a subring. Okay, so let's see how. Let R be a ring of characteristic 2, and let D be the set of all idempotents in R. And let's also write in detail what that means, i.e. D is the set of those elements in R such that if you square any one of them, then you get the element back. That is the definition of an idempotent element. Now we have to prove that this D is a subring of R. That is, under the operations in R, addition and multiplication, D itself forms a ring. So we will start off by showing that D is a subgroup of R under addition, because that is part of the ring structure. But even before that, D must be shown to be non-empty, because any algebraic structure on a set is, by definition, the structures we have so far seen, they are defined only on non-empty sets. Okay, so let's see how D is non-empty. R is just given to be a ring of characteristic 2. It is not given that R has a unity. R may not have a unity. Okay, but so in spite of that, there is one element, of course, which is an idempotent, and that is the 0 element in the ring R. Since 0 square is equal to 0, we have 0 in D. So D is non-empty. Now you choose two elements in D. Let A and B belong to D. Then the square of A is A and the square of B is B. Now we want to prove that both A plus B and minus A are in D. So that means the squares of these elements also have to be shown to be themselves. Now let's see how. What is the square of A plus B? Because we are in a commutative ring, the usual binomial theorem holds, and we can write A square plus 2AB plus B square. Had this ring been a non-commutative ring, you would not have been able to write this. Instead, in that case, you would have to write A square plus AB plus BA plus B square, and you don't know whether AB is equal to BA. For some pairs, they may be equal, but because the ring is non-commutative, there will be some pair of two elements where AB and BA are different. In this case, however, it is commutative, so the usual binomial theorem holds. But now note that A square is A and B square is B, and this is 0 because the ring has characteristic 2. So 2 times anything, that means you take a ring element and add 2 copies of it, you are going to get 0. That's what characteristic 2 means. So that's why we have A plus B. You can write one small explanation here. Note that 2AB is equal to 0 due to the ring being of characteristic 2, of course. So this is one thing. And what about the square of minus A? Using your usual ring properties, this is actually nothing but A square. But A square is equal to A, and A is equal to minus A. Why? Because 2A is 0. So here also we write one such small explanation. Note that 2a is equal to 0, which is why we are having this. So we see that the square of a plus b is a plus b, and the square of minus a is also minus a. So a plus b and minus a both belong to D, and thus D is a subgroup of R under addition. So D is a subgroup of R under addition. Now what else do we need to show that D is a subring? Only that D is closed under multiplication, because the other two axioms, that is the multiplication is associative and the two distributive laws are true in general in R. So in particular inside D also they are going to be true. So the only thing we now have to show in order to prove that D is a subring is to show that D is closed under multiplication. So for that we now calculate the square of AB. We now need to show that AB also belongs to D, but this is rather easy. Also, the square of AB is a square b square, and here we are using the fact that the ring is commutative. Here also we have used it. Otherwise, in a general ring which may be non-commutative, AB square will be AB, but not necessarily this. But A square is A and B square is B. And so, AB belongs to D. Thus, D is a. Now, finally, we can conclude that this is a subring of R, and that was the thing we wanted to show. And next, let's see this one. Describe the smallest subfield of the field of real numbers that contains root 2. Describe the smallest subfield of the field of real numbers that contains square root of 2. And it has been explained what smallest means in this case, that is, although we surely know what that means, but still, describe the subfield K with the property K with the property that K contains root 2, and if F is any okay. K contains root 2 and any subfield, and if F is any subfield containing root 2, then F contains K. In that sense, it's the smallest, K is the smallest. So let's see what that can possibly be. Perhaps you already know how that subfield looks, but here it is. Let K be the set of all real numbers that look like this, a plus b root 2, where a and b are coming from Q, the set of rational numbers. We already know that square root of 2 is not rational, but a and b are rational, and we are collecting all the real numbers that look like this, a plus b root 2, where a and b are rational, and that set we are calling K. We are now going to show two things. The first is that K is a subfield of the field of real numbers, and the second thing is this smallest nature of K. So let's go through the subfield part first. Clearly, K is non-empty. In this case, you can easily see that not only is K non-empty, but in fact K has infinitely many elements. Sometimes the defining property of a set is so abstract and so complicated that you may be confused whether there is any element in the set or not. In that case, you have to go through some 2 or 3 lines to show that it is non-empty, and then you can say what it is, whether it's a group or ring. In this case, however, it's fairly easy to see. But whether easy or difficult, I keep stressing this fact again and again, because this is something that we tend to forget, and we may end up proving that the empty set is a group, is a ring, or something like that, which is clearly not true by definition. But anyway, here K is non-empty. Okay, so first of all, in order to show that K is a subfield, we need to show that it's a subring. So we have to go through that process that we went through just now, okay, with that thing D. So let a plus b root 2 and c plus d root 2 belong to K, where of course a, b, c and d, these are rational numbers. Then if you add these two things up, what do you get? You can rearrange the things. Here things are particularly easy because after all we are rational or irrational, after all we are just working with real numbers, that's it. A plus c plus b plus d times root 2 using the various field properties of the real numbers, and minus of a plus b root 2 can also be written like this, minus a plus minus b root 2. Now since a plus c, b plus d, minus a and minus b, these are all rational numbers, so we conclude that the sum of these two is in K, and that the negative of any of them is also in K. Note that this fact that if A, B, C and D are rational numbers, then so are these, follow from the corresponding properties of the system of rational numbers, because it's also a field. Okay, so we have now shown that K is a subgroup of R under addition. Thus, just like there D was a subgroup of R under addition, that R was a ring R, and in this case R means the system of real numbers. Thus, K is a, to distinguish that R from this R, we use this font. It's not simple R, it's Blackboard bold R, subgroup of this under addition. Okay, next we have to show that the product of these two is again in K. Next, a plus b root 2 times c plus d root 2. If you just simply multiply the terms out, like you usually do, you are going to get what? AC plus AD root 2 plus BC root 2 plus BD root 2 square, that means 2BD. And now if you rearrange the things a little, you are going to get AC plus 2BD plus from these two terms you take root 2 common out, and that gives you AD plus BC root 2. So again, because A, B, C and D are four rational numbers, so AC plus 2BD and AD plus BC are also two rational numbers. Since AC plus 2BD and AD plus BC are rational, we have this, that the product of these two numbers is also in K. So now we can conclude that K is a subring of R. If you want, you may not write this conclusion, because this is an intermediate conclusion. This is not something we want to show. We want to show that K is a subfield which demands more. But it's a good thing to write such things, because it shows you that you have got the job done to this extent, and then you can think of what else you next have to do. Okay, so to show that it's a subfield, what else do you need to do? You need to show that this subring, because it's a subring, it's going to be commutative. just like R is commutative. So that thing is also over. What else? You need to show that K has the unity of R, which is the real number 1. And further, that every non-zero element has a multiplicative inverse. That is very important. So let's write about commutativity here itself, because we are just writing anyway. K is a subring of R, and hence K is commutative. The unity the real number 1 belongs to K, since 1 is of that form, 1 plus 0 root 2. 1 and 0 are rational, so that's why it is in K. And now finally, let's consider a non-zero element in K. Let alpha plus beta root 2 belong to K such that alpha plus beta root 2 is not equal to 0. Okay. Now, the fact that this has been chosen to be non-zero implies that what I'm trying to say is this: alpha square is not equal to 2 beta square. I have got a little confused here. Let me just see what the multiplicative inverse of this element will be. Okay, that multiplicative inverse, of course, will just simply be the reciprocal of this real number. Now, do we need to write anything else here, or we can just simply start calculating from this point? That's what I got confused about. In the field of real numbers, this is the multiplicative inverse of this non-zero real number. Now the question is this in K? That is the question. Okay. So non-zeroness of this just simply allows us to divide 1 by this. So nothing else needs to be written about that. But, oh no, there is a point. In trying to show that this belongs to K, you will have to do something which goes by the name of rationalizing the denominator. You may have learned about it in school, where what we do if we are given one such thing, then we multiply and divide by the conjugate of this type of number, and that conjugate looks like this, where we just change the sign. Now, in carrying out this step, we need the fact that this is a non-zero real number. This is non-zero, that is our choice. But is this also non-zero? We have to make sure that that is non-zero. Okay, so that's why suppose that this is 0. Suppose this is equal to 0. Then what do we get? Then clearly beta root 2 is equal to alpha. That just immediately comes from this equation. from this supposition. Now you are able to divide both sides by beta in this equation provided beta is a non-zero rational number. We already know that alpha and beta are both rational. If beta is a non-zero rational number, then we can divide by beta. If beta is not equal to 0, then square root of 2 is alpha divided by beta. But since alpha and beta are both rational and beta is non-zero, this quotient alpha over beta is also rational because the rational numbers form a field, and that's why root 2 is rational, which is a contradiction. If you write this much, then all the things are almost written, because they need not write absolutely everything in words. Okay, what I'm saying here is that you need not write that this is a contradiction because we know that root 2 is irrational. Those things are understood. So that means beta cannot be non-zero. Beta has to be equal to 0. Thus, beta is equal to 0. But if beta is 0, then alpha is also 0. Which implies alpha is also equal to 0. But if alpha and beta are both 0, then definitely this is 0. So our very choice of alpha plus beta root 2 has been violated. Which is again a contradiction. Which means what? That this supposition cannot possibly be true. Thus, the last supposition is false, i.e., just like alpha plus beta root 2, alpha minus beta root 2 also is non-zero. Yeah, now we have that. Do you see there are several lines of reasoning from the fact that alpha plus beta root 2 is non-zero to the fact that this is non-zero, but it seems like if alpha plus beta root 2 is non-zero, then this should also be non-zero. Yes, that is true, but there are all these things in between. Now, armed with this new information, we can now carry out that calculation. So this is your usual a plus b times a minus b formula. If you take the square of beta root 2, you get 2 beta square. You need not worry about the non-zeroness of this. It has to be non-zero. Why? Because this is non-zero and this is non-zero, and the product of two non-zero real numbers is non-zero. The field of real numbers, because it's a field, it does not have zero divisors. And now finally this thing can be written in a nice manner in this way. so that we can see the form that it has. It again has that form that the elements of K have. But before we conclude that, we need to see that these two things are rational numbers. Yes, they are. Because alpha and beta are both rational and the denominator is non-zero, so both these ratios are rational numbers. Since this, so the multiplicative inverse of alpha plus beta root 2, i.e. 1 over alpha plus beta root 2 is in K. Okay, we have now finally shown that we have verified all the things that we need to verify in order to conclude that K is a subfield of R. Have we missed anything? Let me just see. We first showed that K is a subgroup of R under addition. Okay. Then we showed that it's closed under multiplication, which makes K a subring of R. Being a subring, it's already commutative because R is a field. Then we also showed that the unity in R, which is the real number 1, it belongs to K. And now finally we have shown that any non-zero element in K has a multiplicative inverse that is again in K. Yes, that's it. Hence, K is a subfield of R. But this much work is not for nothing. You have to now, before you go on to show that K is the smallest subfield satisfying some properties, you need to of course also show that K contains root 2, because that was our primary aim, right? Root 2 also belongs to K because root 2 can be written like this: 0 plus 1 times root 2. So K actually is a subfield of R that contains root 2. Now we go for the smallest nature of K. Let F be any subfield of the field of real numbers such that F contains root 2. We need to now show that K is a subset of F. Now that can be immediately concluded once you know the fact that F contains every rational number. In fact, it's a fact that any subfield of R contains every rational number, and as such, the field of rational numbers is the smallest subfield of R in that sense. Now, I can't remember if we already have proved this fact anywhere in this text or in the exercises that we have seen so far. So what I'm going to do is this. I'm now going to prove it. Okay. It's something that we are supposed to know, but still, let's see how that is true. We now claim that the field of rational numbers is a subset of this subfield F. Note that, so there is something that we immediately note. 0 belongs to, okay, we can write it at once. Both 0 and 1, the rational numbers 0 and 1 belong to F. Why? Because F is after all a field, so it must have the 0 element and also must have the unity of the original field. It's a subfield. Suppose that n belongs to F for some positive integer n. We already have that 1 belongs to F. Now we have supposed that n belongs to F for some positive integer n. You can clearly see where we are going with this. We are trying to apply induction. Then obviously n plus 1 also belongs to F. N belongs to F, that is our induction hypothesis, and 1 belongs to F, that is our basis for induction. So the sum of them also belongs to F, because after all F is a field, so you add any two elements of F, you are going to get another element of F. So by induction, F contains all positive integers. But F is a field, so because it contains all positive integers, it also has to contain all of their additive inverses, that is the negative integers. Since F is a field, it thus must contain all the negative integers. So what is the conclusion now? Now the conclusion is that F contains all the integers. So the set of integers is a subset of F. But now you use the multiplicative structure of F, because it's a field, in a similar manner and conclude that because of this, F also contains the quotients of all integers, where of course the denominator is non-zero. This implies note that just F containing all the positive integers and all the negative integers is not enough. It also has to contain 0. So that's why we have written this separately in the beginning itself. But now this implies that P divided by Q belongs to F for all integers P and Q where Q is of course non-zero. Hence, this is contained in F. Okay, so our claim has now been established, but this is not what we wanted to show. We want to show that F contains K, capital K, for any A plus b root 2 belongs to k, we have a and b in the set of rational numbers by the definition of k. So if now being rational numbers, due to this containment, a and b also belong to f, and already we chose f to be a subfield that contains root 2. So naturally, since all these three numbers a, b and root 2 are in f and f is a subfield, so this has to now belong to f. That's it. We have shown that any element in K is again in F. Hence, K is a subfield of the subfield F. And that's why K is the smallest in this sense. So here the solution ends. You will see more about these things when you study field extensions towards the end of this text. Well, not the end, but when we get to field theory, there we will see more about these things. See, the K, let me just say one more thing before I stop this video. K is sometimes also written like this. It is a subfield of the field of real numbers obtained by adjoining the extra element root 2 to the subfield of rational numbers, and it becomes the smallest subfield of the field of real numbers to contain root 2 as well as all the rational numbers. Okay, you should have this much in a subfield, and the resulting elements coming from the fact that it has to be a subfield in order to contain root 2. You can of course just think of the set containing root 2, which is a subset of R. This is the smallest subset of R, the field of real numbers containing root 2. But this is not a field, it's not anything. In order for this to be a field, you need at least this much. Okay, and that is the idea of field extension. You have the subfield Q of R, you extend that to a bigger subfield so that you have something new, one extra element, and at the same time, the bigger universe still remains a field. You can bring in other things from outside to this also. Say next you can try to adjoin root 3 to this, that can also be done. If you do that, the resulting subfield, which is bigger than even this, will be the smallest subfield of R containing both root 2 and root 3. And these things are related to solutions of, rather I should say, roots of polynomials over fields. Okay, we will see more about these things later on when the time comes. So that will be all in this video for tonight, and tomorrow we have analysis, and yeah, tomorrow there will be a video. I don't think anything will just stop us from doing that. Okay, so tomorrow guaranteed there will be an analysis video, and tomorrow we are going to finish this section that we are where we are at currently. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.